The lift curve is a convenient way to illustrate the properties of an aerofoil under various conditions and in various configurations. The curve plots coefficient of lift, CL, against angle of attack, alpha. You may deduce from looking carefully at this curve that it is for a symmetrical aerofoil, since it starts with zero lift at the axis origin. The curve for a positively cambered aerofoil would actually have its zero lift point to the left of the CL axis, since the zero lift alpha for such an aerofoil is typically -4 degrees. The CL increases with angle of attack up to a maximum CL max, which corresponds to the critical angle of attack, above which lift decreases sharply, a phenomenon known as the stall, which will be covered in detail in a subsequent lesson. There are several important facts that become evident from study of the lift curve in association with the lift equation. To maintain a constant lift force, any change in dynamic pressure must be accompanied by an adjustment in angle of attack. For a constant lift force, each dynamic pressure requires a specific angle of attack. Minimum dynamic pressure is determined by CL max, which occurs at a specific angle of attack, the critical angle, which is between 14 and 16 degrees, depending on the aerofoil. The angle of attack for CL max is a constant for a given configuration. If more lift is required because of greater weight, a greater dynamic pressure, that is, more speed, is required at a given angle of attack. The greater the weight, the higher is the minimum dynamic pressure or speed required for level flight. The lift formula can be used to obtain data which can then be used to apply to the lift curve. But this can only properly be done if the specific values to be used are converted to SI units. To calculate speeds, we need to rearrange the lift formula to read velocity equals the square root of lift over half rho times CL times S. If the aircraft's mass is 60,000 kilograms, we need to multiply that by the force of gravity, 9.81 meters per second squared, to achieve a weight, which will be the same as the lift balancing it. The result is 588,600 newtons. If we convert the other elements, assuming ISA sea level density of 1.225 and a wing area of 105 square meters, using the CL max of 1.532, we now have the equation looking like this. When the calculation is done, the answer comes out as 77.3 meters per second. We need this speed in knots, so we multiply it by 3.28, which is feet per meter, giving 253.5 feet per second. To convert this to knots, we need to make it into feet per hour, which is 912,600, and then divide by the number of feet per nautical mile, 6,080, giving the final answer 150 knots. The same result can be arrived at rather more simply by dividing meters per second by 0.514 to get knots, but we include the steps to show you the logic. Thus, it can be seen that the angle of attack at CL max corresponds to a speed of 150 knots. This method can be used to ascertain the speed that applies to any CL or angle of attack, with a reduction of CL and angle of attack giving a higher speed. Aerofoils of differing sections and thicknesses will produce different lift curves. A symmetrical section of 12% thickness will give a curve that starts from 0 on both axes. In comparison, the curve for a symmetrical aerofoil of 6% thickness shows that it will produce less lift at any given angle of attack and reach its CL max at a lower angle of attack and at a much lower value than the 12% section, which has a CL max some 70% greater. If the 12% section were to be cambered, its curve would move up and to the left. Up meaning that its CL max would be higher. The reason for this is that the section's stream tube has a smaller cross-section, giving greater acceleration and thus higher pressure differential. The curve's move to the left indicates that, at 0 degrees angle of attack, the aerofoil is producing lift. Zero lift is achieved typically at around -4 degrees with a cambered aerofoil. The reason for this is that, even below 0 alpha, the camber creates a smaller stream tube cross-section than a symmetrical section, and therefore generates a small amount of lift. The different types of aerofoil sections we have just looked at have various advantages and disadvantages. We have already seen that CL max may be increased by both camber and thickness. The importance of CL max is obvious. The greater it is, the lower is the minimum flight speed or stall speed, VS. However, the thickness and camber required for the low VS will also produce more form drag and larger twisting moments at high speed. A high CL max is only one of the requirements for an aerofoil section, but its main point is that it gives a low minimum flight speed. With the low VS comes the penalty of a low efficient cruise speed, because of the excessive drag generated. It is thus better to use an aerofoil that is efficient at a high cruise speed, with the ability to increase camber temporarily when it is necessary to fly slowly, such as on the approach. This can be achieved by the use of hinge sections of the wing trailing and leading edges, collectively known as flaps. The lift curve can be used to gain useful information about an aerofoil's characteristics, and, when used in conjunction with the lift formula, can give further useful data. The lift curve will be seen again soon in the lift lesson, but in combination with its counterpart, drag curve. As you will see, drag is inseparable from lift.